And welcome back as, of course, we continue our cosmic journey looking at stars. We, of course, have talked a little bit about some of the spectra of stars, but let's go ahead and use that now to measure the stellar radius, composition, even motion of the stars. So let's start this off by kicking off to think about the clues that we need to find the size of a star. Well, we know that stars come in a wide variety of sizes. And at some periods in their lives, stars can expand to enormous dimensions. Stars of such exaggerated size are typically referred to as giants. Stellar spectra can actually be used to distinguish giants from our more run-of-the-mill stars. So suppose you want to determine whether or not a star is giant. Well, a giant star has a large extended photosphere. This is a hydrostatic equilibrium trying to reestablish itself. Now, because it is so large, a giant star's atoms are spread over a great volume, which means that the density of particles in the star's photosphere is low. As a result, the pressure in a giant star's photosphere is also low. And this low pressure affects the spectrum in two ways. First, a star with a lower pressure photosphere shows narrower spectral lines than that of a star of the same temperature with a higher pressure photosphere. The difference is large enough that careful study of spectra can tell which of the two stars at the same temperature has a higher pressure and which one has a lower pressure. This effect is due to the collisions between particles in the star's photosphere. More collisions lead to broader spectral lines. Collisions will, of course, always be more frequent in a higher density environment. You think about our own sun, when we talked about the core of the sun and how long it takes photons to be able to escape because it's so packed in that radiative zone that those photons bounce around. Second, more atoms are ionized in that of a giant star than in a star like our own sun with the same temperature. The ionization of atoms in a star's outer layer is caused mainly by photons, and the amount of energy carried by those photons is determined by temperature. But how long atoms stay ionized depends not on temperature, but in part on pressure. Compared with what happens in our own sun, which is relatively dense photosphere, ionized atoms in a giant star's photosphere are less likely to pass close enough to electrons to be able to interact and combine with one or more of them, thereby becoming neutral again. Ionized atoms have different spectra from atoms that are considered to be neutral. And so we can use the abundance of elements to help us really determine more stuff. So absorption lines of the most known chemical elements have already been identified in the spectra of the sun and of stars. If we see the lines of iron, for example, in a star's spectrum, then we know immediately that the star has to contain iron. Note that the absence, though, of an element spectral line does not necessarily mean that the element itself is absent. The temperature and pressure in a star's atmosphere will determine what types of atoms are able to produce absorption lines. Only if the physical conditions in a star's photosphere, such as that lines of an element should be then there, we can conclude that the absence of observable spectral lines implies a low abundance of that element. Now, studies of stellar spectra have shown that hydrogen makes up about 3/4 of the mass of most stars. It's the most common element in the universe for a reason. Helium is the second most abundant element, making up almost 1/4 of stars' mass. So together, hydrogen and helium typically make up anywhere from about 96 to 99% of the star's mass. Now, about 4% or less of heavy elements such as oxygen, carbon, neon, iron, nitrogen, silicon, magnesium, and sulfur are present, and these are typically among the most abundant and common within stars. Now, generally, but not invariably, the elements of lower atomic weight are more abundant than those of higher atomic weight. Now, any elements other than hydrogen or helium are referred to as metals. Now, this is not metals as the definition we know, but rather anything that's simply not hydrogen or helium. So when we're talking about stars, anything not hydrogen or helium is a metal. Now, the fraction of a star's mass that is composed of these elements is referred to then as a star's metallicity. So the metallicity of the sun is 0.02, since about 2% of the sun's mass is made of elements heavier than helium. Some very rare elements, however, have not been detected in the sun, but instead have been based on laboratory elements. The next piece to really look at as we start understanding about the sun is radial velocity. So when we are measuring a star, or particularly the spectrum of said star, we can determine the wavelength of each of its lines. If the star is not moving with respect to the sun, then the wavelength corresponding to each element will be the same as those we measure in the lab here on Earth. But if stars are moving toward or away from us, we actually have to consider the Doppler effect and how it might be shifting things. We should see all the spectral lines of moving stars shifted toward the red end of the spectrum if the star is moving away from us, or toward the blue or violet end if it is moving toward us. The greater the shift, the faster the star is moving. Such motion along the line of sight between the star and the observer is what we refer to as radial velocity and is usually measured in kilometers per second. Now, radial velocity measurements of double stars are crucial in deriving stellar masses. When the spectral lines of a moving star shift toward the red end of the spectrum, we know that the star is moving away from us. If they shift toward the blue end, then the star is moving toward us. And we can see that here in our Doppler shift image. We have right here a red shifted image, a stationary blue shifted. So the stationary is kind of that neutral zone. You can see if we shift red, all our lines here are to the right of how they are in the stationary. And in the blue shift, they're all to the left of the stationary. And so this gets us to the idea of proper motion, which is another type of motion stars can have that cannot be detected with stellar spectra. Unlike radial motion, which is along our line of sight, proper motion is transverse, which means it is across our line of sight. We can see it actually as a change in the relative positions of the stars on the celestial sphere. Now, these changes are very slow. Even the star with the longest proper motion takes 200 years to change its position in the sky by an equal amount to the width of the full moon, and the motions of the other stars are smaller yet. So, for example, here we can see in this image, there's 1985, 1995, and 2005, how the star has, of course, moved across the night sky. Now, we measure the proper motion of a star in arcseconds, or 1/3600th of a degree per year. For this reason, with our naked eyes, we do not notice any change in the positions of the bright stars during a human lifetime. If we could live long enough, however, the changes would become rather obvious. For example, some 50,000 years from now, terrestrial observers will find the handle of the Big Dipper unmistakably more bent than it is now. And we can see that here, 50,000 years ago, the kind of shape of the Big Dipper. Here it is today, and here it will be 50,000 years from now. Next is space velocity. To know the true space velocity of a star, its total speed and the direction in which it is moving through space relative to the sun, we have to know its radial velocity, the proper motion, and distance. Now, a star's space velocity can also, over time, cause the distance of the sun to change significantly. Over several hundred thousand years, these changes can be large enough to affect the apparent brightness of nearby stars. Today, Sirius in the constellation Canis Major, the Big Dog, is the brightest star in the sky, but 100,000 years ago, the star Canopus was the brightest star. And a little over 200,000 years now, Sirius will have moved away and faded somewhat, and Vega, the bright blue star in the constellation Lyra, will take its place as the honor of the brightest star in Earth's skies. Now, this figure shows the true space velocity of a star. What we see is that the radial velocity is the component of the space velocity projected along a line of sight from the sun to a star. The transverse velocity is a component of the space velocity projected onto the sky. What astronomers measure is the proper motion, which is the change in apparent direction on the sky measured in fractions of a degree. To convert this change in direction of a speed, it is also necessary to know that the distance from the sun to the star. Now, the Doppler effect is very useful, of course, for determining spectral shifts, but we can also use it to measure how fast a star rotates. If an object is rotating, then one of its sides is approaching us while the other is receding, unless an axis of rotation happens to be pointed exactly toward us, think very much like Uranus. This can be the case for either the sun or a planet, or even a farther off celestial body. We can observe the light from either the approaching or receding edge of those nearby objects, and directly measure the Doppler shifts that arise from the rotation. Stars, however, are so far away that they all kind of appear as unresolved points rather than as fixed things we can latch onto. So for right now, this is the best we can do to analyze the light from an entire star at once. Now, due to the Doppler effect, the lines in light that come from the side of the star rotating toward us are shifted to shorter wavelengths, and light in the light from the opposite edge of the star are shifted to longer wavelengths. If a star is rotating rapidly, there will be a greater spread of Doppler shifts, and all its spectral lines should be quite broad. Now, the amount of broadening we refer to as line broadening can tell us the speed at which the star rotates. And again, we can see that here in our image here. So when something's not rotating, you can see how the lines all are. Whereas when we have the rotating view, you can see here we have the shorter lines, the medium length, and then the longer lines here, which then, of course, affect the spectrum. You can see here we have one kind of narrow region here, but here our darker region is much thicker. So measurements of the widths of spectral lines show that many stars rotate fast as the sun, some with periods of even less than a day. Now, these rapid rotators spin so fast that their shapes are kind of flattened in what we call oblate spheroids, so they're not quite ball-shaped. Now, studies have shown that stars can actually decrease their rotational speed as they age. Young stars tend to rotate very quickly with rotational periods of days or less, whereas very old stars can have periods of several months. And we can see that here with Altair, who has a rotation period of about 6.5 hours, whereas the sun is about 24 to 30 days.